Okay, hello everyone. A warm welcome from my side. My name is Dominik von Opdenbosch. I'm from the Chair of Media Technology from the Technical University of Munich. And today I would like to present my work on efficient map compression for collaborative visual SLAM. I'd like to spend a few seconds on the motivation slide here. So actually what I'm working on is a project that aims to explore the Mars. So in more specific, we target the Valles Marineris canyon system, and we want to explore the environment by using rovers, but also climb into steep craters and caves using a hominid robot platform. So what we target here is a long-term exploration using visual features, so a visual SLAM system, and also using multiple agents. So we have rovers, we have robots. Also, we have a mission control that is responsible for archiving all the information, evaluating all the information, and send it back to Earth. So that's why we address the issue of map exchange between different agents. So on the left-hand side, you can see here the basic setup. We have multiple agents that have a camera inside that run a visual SLAM system, and they're somehow connected through a network with other agents and also the mission control, and the goal is to efficiently exchange the map information obtained from each individual agent. So our proposed map compression module consists of two parts. So the first one is a lossless compression scheme, which exploits visual similarities between observations of map points obtained from a visual map. This enables collaborative mapping and also archiving the data for later inspection. And the second part of the proposed map compression module is the lossy compression, where we remove uninformative points from the map so that we can prevent unbounded growth of the map during long-term operation. So for the lossless compression, we make use of the geometric structure of the obtained visual SLAM map. So usually we have a map point, and this map point has been observed from multiple keyframes. So multiple features, in our case orb features, observe or describe the same map point and are associated with it. So what we propose is to link all the observations using a graph structure, where the graph is defined as the edges between the observation, and the weight of the edges is defined as the Hamming distance. We make use of differential feature coding, so we build a minimum spanning tree connecting all the observations of a single map point and encode only the information, so the visual features, differentially. At the first observation of a map point, we use a visual vocabulary to store the visual information for the first observation differentially to a visual word. For the lossy compression part, we tightly couple the compression and the removal of feature points by using the bits per map point Q as costs in the optimization problem for the map sparsification, so removing unnecessary information. We do this by using an integer programming problem, and we formulate this by using several side constraints. For example, that each keyframe has a certain number of map points that are visible in this keyframe. And then as we have the exact number of bits we need to spend to store one map point, we can exactly define how large our resulting map should be, and then we can run this optimization problem to reduce the map at this specific target size. Here are the results. So we evaluated the approach using the OrbSLAM2 framework on the EuroC dataset, and here we have different representation of the map. So on the left-hand side we have a full map, and on the middle, on the right, we have maps which are compressed to 1.5 megabyte and 0.5 megabyte per map. And the color coding here in red are map points that have been observed multiple times from different perspectives, and black that have been observed not that often and therefore are removed in the reduction step here. For the lossless map compression, we can achieve a reduction to 39% of the original map size without losing information. And for the lossy map compression, we can compress down to 91.7% while maintaining similar relocalization capabilities compared to the full map. So that's all from my side. We have a website where there's a video showing our system, and I would be glad to answer all your questions at the poster session this evening. Thank you very much.